Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about powdered metallurgy or PM for short. So let's dive deep into it. So what exactly is the need for this sort of powder metal technology? Well, reality is that we need a lot of metal part, and it does not mean just cars or washing machine or bottle making plants or basically everything needs bonkersly large amount of metal parts in different stages and in different properties, because you may require like a hard metal for one requirement, another maybe a bit more ductile metal for something else. So not only we have a variety of sizes, we also have a variety of requirements for properties. And on top of that, mass production is the key, because whenever you see, okay, there is this car factory that is producing, let's say, one car per minute. Well, you have to understand it's also consuming bonkersly large amount of sub-assemblies from other places, be it gearbox, be it engine blocks, be it some hinges, be it doors, whatever have you. So bonkers amount of material goes in, only then you get bonkers amount of mass production. So whenever you're saying, okay, we are getting cold drinks for cheap, how can you do that? Well, because somebody has invented a machine that does that. So that machine requires bonkersly large amount of component. So we need a supply chain for the supply chain itself. So mass production is the key. Now you have to understand, whenever we are building something in your household or whatever have you, we are going through what we call prototyping. So we do not care too much about waste material. So you can see YouTubers who are like, okay, I'm making this metal gear, I'm gonna CNC this and all that. That does not sound stupid. Logical, and that's exactly how human industrial revolution started. However, the moment you scale that up, like let's say they built a gearbox and you're like, okay, now let's make 1 million of these. Yeah, that wastage will pile up so much that company will go bankrupt just because of the wastage. And again, that explains why the heck in industrial revolution, in principle, we could have built everything that we have right now. It's just we did not have a cheap technology of mass production. Waste is not acceptable. Material wise, it's not acceptable. Remove the environmental cost. Just throwing away metal, or even if you're like, oh, we're going to recycle it. Recycling is not free. You have to spend energy on it. So wasting material is unwise, the want not, waste not kind of scenario. So you need something that can be mass produced without creating bonkers amount of wastage. That's first thing. Another aspect, as our technology improved, we started to go into what we call CAD. Or again, back in the old days, we also had mathematics on paper. Now, problem with that is that's infinitely precise, right? Like you can draw this circle is perfectly precise to, let's say, well, perfect. This is like 1 inch diameter. It is 1 inch diameter, but in real life, that's not how it works. So you also have to describe what we call tolerance. So tolerance would be described in such a way that plus and minus 0.5%. That's a sloppy part. And then you're like, no, this is the airplane part. It has to be high precision. So it could be like 0.01% plus and minus. So that's how you describe tolerance. But so what does that mean? That simply means anything that you are mass producing must also meet accuracy. When you say that, let's say this part is like this size, it has to be within tolerance, whatever the tolerance requirement by the process. So tolerance must be required. And that thing is needed in every field, be it computer power supply, to basically your satellites, to cars, to washing machine, to dishwasher, to every Tom, Dick and Harry. So we have bonkersly large amount of needs. Thankfully, powder metallurgy is here to save us. The idea is very simple. It reduces waste. For example, you are making a part, instead of doing the CNC milling thing, you are just like, hey, let's stamp the part. So you are stamping the part with powder rather than sheet metal. You are using powder to that. Now, here's the benefit. If done correctly, one stamp, that's it, done, go home. That's the final shape. The shape will not change. So you take your powder, stamp the hell out of it, and voila, you get exactly the right dimension within the tolerance of the mold, of course. And again, how precise the mold would be, that will directly depend on the requirements. So you get per time, done. Part is done, sorted. Dimension is sorted. You do not have to worry about dimension. Again, you do not have to take it, then grind it, then polish it. No, tick, done. So that's a very serious advantage. On top of that, the porosity, because again, you're talking about powder, you're talking about pressure, so you can control how voidful it is. Meaning, if you're like, hey, this is a lightweight part, it does not need to be like, carry the weight of the world. So it's like, let's keep it light. So how much pressure? You're like, let's just chill it. And you're like, no, this needs to be like aerospace grade, like we need some oomph to this. Then you increase the, basically decrease the porosity, and then you will have stronger part. You get to control this factor. You do not want to overspend. And again, it does pile up. If you ever wondered how the heck Chinese can manufacture something so large scale for so cheap, their porosity is different. So same company, basically same assembly, so to say, could be making parts for like, German engineering system, and porosity would be here, and you're like, same stamp could be used for like, Chinese stuff, and it's like porosity is here. Looks the same, mold is the same, it's just like porosity is not the same. So porosity is a controllable vector, which again, I'm talking about the worst case scenario, but there are genuine reasons why you want to control it, and that is controllable. And this puppy, the biggest advantage of it, it is fast mass producing, meaning you can see how quickly you are producing a metal part. It's like ting, 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 ting. Nothing comes close to this. And this is a very small scale where you have just one stamp doing this. Most times you will have like a giant assembly going vajang, vajang, vajang. You can mass produce like crazy high speed. Like this plant unit will not be the bottleneck. Like every machine other than this will be the bottleneck. This is like, bro, if you can feed me powder and if you have the hydraulic energy needed for this, me good. Like there is no inherent, like CNC, it takes time. Like they have to spend the time. Like each gear could be like, few hours to few days. Yes, there are some systems. And again, if you're polishing and grinding, yeah, good luck. But here it's like, but done, take it and go. I don't have time for this. That's how quick this is. Meaning this can be on the back end of whole of Germany's automobile industry, and this like, I got this. Those factories will be so slow part, not me. So it's very, very fast. That is a general thing. And all of this can be done economically. Physics, engineering, economics. So this is not that complex. It's not like plasma vapor deposition or like this and that. It's like, it's easy, relatively speaking. And like if you have even a rudimentary industrial revolution level technology, you're like, we got this, man. We good. So that's why we are so desperate for this technology. So let's start with the beginning. You take the powder and you make a very precise mold. The mold directly controls your final dimensioning, and you have to decide how much you want to spend, like 0.1% plus and minus, 0.01% plus and minus, or like aerospace grade 0.001%. God help you. So that's up to you. The mold has to be designed like that. Now you put powder in and you pack it. Now, how much pressure you're talking? You are talking about metal powder here. So you have to understand, metal has a lot of oomph, even on a grain structure. It is like, it's not easy. It's like, I got this. Heck, I'm pretty sure if you put a sand there and just compacted it, sand might just melt just because of the compression energy. So you have to understand, you're dealing with metal powder, so a lot of oomph has to be put. How much oomph we are talking about? You're talking about 10 to 60 ton, or sometimes even more than that, per square inch. That's a seriously large amount of pressure. So you do this, you compress it, you make a mold, you put the powder, you compress the hell out of it. And like 10 to 60, and that's the starting point. You can go higher than that. You start that. Now, here's the deal. If the aspect ratio is long, meaning width-wise, it does not matter that much. The length-wise, like depth, if it's long, like you need a high aspect part, like 1 inch by 10 inch, yeah, then you need to compress from both ends. Because if you do not, problem would be, because it's powder, the energy has friction to it, right? Like you are putting a lot of pressure, the particles will try to go this side also, but again, there is a wall there that's pushing it. But many times they will like, create a crust layer, so to say. The crust would be super hard metal and the center would be like very soft. But here's the deal, that may be desirable, but here's the deal, once you are doing long aspect, you could literally have a brittle part in the center. Like literally the top part is like ultra hard, bottom part barely, it could be a powder, because the energy did not transfer that well. So whenever we are talking about long aspect parts, we compress the both from bottom and top, so that powder has enough chance to actually compact into the size that you're looking for. Now again, that's not that difficult, but again, it's not suitable for super duper long aspect parts. Like 1 to 10, okay. 1 to 20, what the hell are you doing? 1 to 30, yeah, people will laugh at you if you try to do that. So it does have a limitation in that regard, where it's like you cannot have hyper long aspect ratios. But for more than enough part, it's like, bro, I got this. And for low aspect ratio part, this is like, I'm good. So and you do double side pressing if you need longest complex parts. Sort of like, for example, this sort of bearing race where you need this sort of cutouts, you can make it, machine it, or you're just like, hey, just make a mold for it and just compress from both sides. Ta-da! You can do that. And here's the deal. What about the parts that come out of this? The parts are very green. That's the technical term, green parts. So basically it's weak. If you do like this, it will shatter. It's just a part strong enough where it's like a bond is loose enough and strong enough where it's like, it's almost like a sand castle. I'm pretty sure you must have been child at some point. You must have built sand castles. It's like that. It's good enough where machines can move it around. You do not have to baby it, but it's not like, it's not that, not yet. So this is the pressing stage. Majority of your work is done. Then we come to sintering. the black magic part. So this part you cook. Now here's the deal. You control the environment. So you control the hell out of it. So temperature. Now temperature, whenever you are talking about metal, you have to understand metal do not like to go through shocks. You cannot just go 800 degrees Celsius, 0 degrees Celsius. Yeah, it's going to fall apart on its own. So you need to control the temperature. Not only how quickly it rises, but how quickly it cools. Both of them directly controls how strong your part would be and how its property will be. You could literally have same gear for, let's say for some reason you want a different requirements out of it. You can have same machine, just by changing the temperature ramp and down, you can change the hardness. So we generally take bare minimum 3 steps. One is preheating. You do not go from room temperature to like ultra hot temperature. You're like, let's warm it up. Let's boil off volatile gases from it and things of that nature. Then you go to high heat, like the main work, and then you cool it down. And you do not shock cool it. Like, cool, bro, cool. All of this has to be controlled. Now that's the temperature vector. Now what about the atmosphere? Where this is happening? Well, here you have simple option, vacuum, pull the vacuum on it. Why? Well, nothing else there is to contaminate it. That's desirable. But again, then question, how would you heat it? Again, you could use electricity to heat it, induction to heat it, infrared lamps to heat it. You have options. That is one tool. Another tool, which again you have to understand, you are talking about metal powder exposed to the atmosphere, it will rust like crazy. So how do you take care of it? Well, you oxidize it, oxidize the rust out of it. Like how? Well, whenever metal gets hot, it becomes very horny, so to say. So it takes oxygen from the atmosphere. But here's the deal. That state is horny in both direction. Basically, oxygen can leave also that quickly. So what if you seal that and you dump hydrogen there? High temperature hydrogen is very reactive. What is more reactive to oxygen? High temperature hydrogen or metal? Metal is not. Yeet. Basically, you can literally leach oxygen out of it. Basically, you're like, no, give me all the rust. So that's how you can remove rust that is being formed. If your part is very sensitive to oxygen contamination, hydrogen is like, I got you, fam. I can remove all the oxygen there. So that's one atmosphere option. Another option is carbonizing atmosphere. Now, like, why would you want to inject carbon? Well, imagine you have this puppy, super awesome gears. Now, but you know anything about gears? Gear go through a lot of abrasion. There's like, so you want the surface to be hard. Again, depending on the requirement, you may require it, you may not. But if you do require it, you're like, what if we can temper? Like, what if we can infuse something into it to make it hard? Well, how about carbon? How about you inject carbon on a molecular level to the surface, to the outer surface? Well, you inject basically methane there, CH4. Now hydrogen is yeet, hydrogen yeets out of the carbon is like, what the hell, where else can I go? Metal is like, I will take you. So it infuses from outside inward. So, and this also solves the very critical problem. You do not want metal to be super hard because it becomes like a glass, brittle. It can crack very easily. And yes, metal do crack. So you want harder, basically, let's say it's a bolt. You want the threads to be as hard as possible. So it's like, I got this. But here's the deal. If it is really got this, you tighten it, it will shatter. It will just like, put. So you make sure that does not happen. You want the core to be like, hey, softy, that's like a ductile. I got this. I can stretch. I can take some load. So this way you achieve that. You are like outside surface, hard, strong. The core, I got this. I can take some abuse. So that's one option. Another super simple option is just put nitrogen there. You do not want atmosphere there because oxygen will destroy your parts. So you may not even want carbon dioxide. So just flush it with nitrogen or argon and forget about it. So you have options. That's the whole point. You're controlling how each batch is working. And what about the temperature? While they do look glowing hot, that's how hot they go. They never cross the melting point. So you use a metal powder, they will have a temperature. It's like, hey, at 700 degrees Celsius it melts, you will go to 650 or maybe 600. You never cross that melting point. You do not go into metal. You do not do phase change. That's the first again. Thou shall not do phase change. Now, like, okay, what happens then? Well, dimension remains intact. That's good. Another aspect, this happens on a molecular level. So all the boundary layers where grains were touching each other, this heat process allows the grains to diffuse through each other. Basically, the voids disappear. Now, it does not disappear as in like, again, there is not enough material there, but all the grains that were touching, that border disappears. It's just like, it disappears into each other. So now you have a metal part that would be similar to the cast metal that has the same porosity. So if, for example, if you're casting, like poured metal into a system and that mold was not very high quality, or you did not have enough de-aeration to it, it may have voids, like how people pour resin and it could have gases trapped into it. Same happens with metal. Again, that will have a X amount of strength. This will have exactly the same. The only way to beat that is like if you have very high quality, like very high quality forge part, or hammered parts, like take a part, hammer the hell out of it into the shape, then it's like, yeah, all the porosity that even if it will form from a pouring liquid pouring stage, it will be removed out of there. That part is the only thing that can exceed the strength. Now be mindful, porosity is a control factor. You could still, hey, I did all the process, the parts are still fragile. Again, go back to the last stage of the pressing part. So if we send a part that has like 90% or 95% porosity, basically void reduction, here the output would be indistinguishable. That will be very clear. For all practical purposes, it will be indistinguishable. And given the fact that you can control the properties of it, you could be like, hey, I need ultra hard coating on the outside. This will beat almost all other options. And yes, these are used in aerospace, military, and those sort of things. So degree Celsius must be below liquid. Basically, phase change is not allowed. You must be below phase change, and the powder bonds to each other. So this is stirring. 2 parts done. So that's why we are so excited about it. Like, it's mass production. You tailor the properties of it, and you're done. Done. There is nothing more to it. It's just there is no polishing, no grinding. Done. Go home. So we can tailor the hell out of it. This is a very tailorable, process. It's a very flexible in its execution. You can literally, hey, I want like, this deep carbon layer injected into there, so it's like ultra hard or lubricating. So you can do that. And increased porosity is a way to save weight, which again, some people abuse the system. That's why it's known that, oh, the parts do not like, yeah, it's like not done correctly, or to be fair, done precisely as it should be in order to save money. So that could be the option. Other times it's like, hey, we want the part to be light, that's why we are not spending. And again, if your motor, let's say, has 1 horsepower rating, you are not gonna waste your metal powder on a stuff that's like, it can handle 10 horsepower. It's like, bro, 1 horsepower motor, let's put 2, factor of 3, let's say, let's go with 3. You're not gonna put 10. So again, if done correctly, you will never notice it, but they will save money. That's the ideal outcome. And that's a very good vector. On top of that, solid lubrication is possible now, meaning because you are infusing or just basically compacting powder, you can put anything in there. For example, you can put graphite in there, you can put molybdenum disulfide there. Now, like, aren't they lubrication? Yes, that's the whole point. Have you ever noticed that we no longer live in a world where we have to oil the doors? Like your car doors, you do not require to oil it. Why? Well, these are used there generally. A flange, so to say. It's a basically solid state bearing. So inside, because again, it's a low RPM scenario, but it does require to last for decades, so to say. So it's like, what if the material wears down? Okay, that's not a good thing, but what will fill in its place? Well, what if there was lubrication in the material itself? Ta-da! Solid lubrication, what we call self-lubricating bearings, flanges, so to say. So self-lubrication, you do not have to worry about it. It will literally wear, like if it wears, there's graphite there. So if you want to look into a microscopic layer, it's like, okay, there's a metal grain, there's a graphite grain, metal grain, graphite grain. You wear it down. Okay, another graphite grain, another metal grain. It never runs out until the parts wears out. But you have to understand, these things saved our bacon. Like, shut up, take money. All car industry just like went cuckoo on this. Many places have this, by the way. So this is just, I'm saying, like the fact that we can do this. And another aspect is porosity. You may think like for gearbox that may not be desirable, but again, it also has one of the advantage, because on a molecular level, there is voids there. That void can easily absorb liquid oils. It could easily absorb grease. Benefit is, whenever you're talking about gears to gear contact, it's only contacting a very small patch. But whenever you're talking about like forged or machined gears, they literally like, squish grease out of there, squished oil out of there. So that part does not get that much protection, or you may require like a high pressure oil pump to pressurize it. But here it's like, hey, everything is there. Everything is infused with each other. You do not have to worry about it. That's like for many specific engineers, that's the reason why we can have like, brushless drill motors. You could have done that long ago. It's just the gearbox would not have lasted. But now we have gearbox that is made out of these. The porosity allows us to have enough lubrication, lithium lubrication specifically. That's like, we good. We got this. That's the carbonizing atmosphere. Again, that's like this specific thing that you can make a gear part in millions per day kind of scenario, and you can control how hard the outside surface is while going through a process once. That's like, damn, that's like, shut up, take money. That's awesome. So that's there. Diffusion. And again, I'm just telling you one option. There are people who do PhD on this. They're kind of like, okay, we get you. Like, we can control this much depth. We got you, man. We can fine tune it on a molecular level. We're good. Now, what if all this is like, okay, but you want a part that's like GG, like there is no discussion, you want a GG part. Well, we have hot isotropic pressing, basically this puppy. So you take your part, You compress as hard as you can, no void. You're trying to achieve what we call zero void. Then you put in here, you seal it, you pull the vacuum on there, then you flush it with basically inert gas, generally argon, and you pressurize the hell out of it. And I mean pressurize the hell out of it. Generally these are done for high temperature alloys, so you could be going as high as 1500 degrees Celsius, and PSI wise 30,000 PSI. You're going bonkers in terms of, basically it's almost diffusion bonding it. Now what's the benefit of this? Well, the parts that come out of this is so strong that even if you're talking about a liquid casting part, those part has to send here to compete flat out. Like if you are doing this process on your powdered metal part, yeah, that's done. The reason we don't do it for everything, it is expensive. Not only the chambers, like you have to understand, chamber that can handle 30,000 psi, it's like, that's not cheap. And again, having argons, electrical heat and all that, it's expensive, it piles up. But again, what do we use this for? Right now, the primary use cases are medical implants and my personal favorite, jet engine turbines. The turbine blade, how do you make it? Well, powder allows you to make whatever shape you want. Cool, awesome. How do you make it hard? Cook it, extra hard. So that's how you get the ultra strong part. Like there is nothing that exceeds this output. Like only in hyper niche scenario, there is something that could even come close to it. But realistically, once you are having part out of this, you are looking at the upper limit of material science. Like that's it. There is nothing more than this. So this sort of tailoring option is shut up, take money. So this was my presentation on powdered metal gear parts. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.